Okay, right now with this, the first initial version of the position specific scoring matrix, we have our weights directly written as the frequencies, and therefore the weights that we use to to combine those match mismatch scores are they are like this. Okay, whatever the frequency is, we are using something a linear weight like this. What we may want to do is we may want to do something similar to this one because when the frequency gets higher, we may get, for example, a larger weight compared to, for example, if you take a look at in the previous case, I mean in this initial case, when you look at this, if the frequency is, for example, 0.2 and 0.8, 0.8 here, the weights are exactly 4 times. Okay, so if this is if the weight is W here, it's going to be 4 times W here because there is a linear function of the frequency. Now, if you want to do something like this, in which when it comes to 8, we are going to have much larger weight than what we have at 2. So if you have some non-linear weighting scheme like this, as you can see, when it's 0.2, it's much lower than this W, and when 0.8 is much higher than this 0.8. So you break the linear relationship between those two. And one way to obtain this is you may use the logarithm directly, the logarithm of that frequency. But that's a problem, right? Because these frequencies are numbers smaller than 1, so they're going to get negative weights. So they're going to be negative because the logarithm of a number smaller than 1, I mean logarithm of 1 is equal to 0, and logarithm of numbers between 0 and 1, they are negative numbers from minus infinity to 0. So we are going to have negative weights. So in order to break these, get rid of these negative weights, one way to do is to divide it with some other negative number. Okay, but what happens is that when you divide it with another negative number, for example, you can take a logarithm of small number, and if you want this to be a large weight, you may write here, for example, if we take, for example, logarithm of 1 over n, indicating the smallest amount of frequency we can have if a residue occurs in that column at least once. Okay, so this is the smallest frequency. You take the logarithm of that smallest frequency, you take the logarithm of the actual frequency, and if you take this ratio, you're going to get your actual weight. So the W's are going to be defined in such a way that the logarithm is weighted by the ratio from the actual frequency over the logarithm of the smaller frequency. By the way, these formulas, they are all heuristics. There is nothing biological behind them, right? I mean, they're just somebody thrown into this idea, okay, maybe better to just weigh these sequences, not just we want to get rid of this linear scaling because more frequencies like 8%, I mean, having 2%, 20% of something is like noise, all right? So we just want to ignore this. I mean, 80% may contain much more information. It's not just 4 times more, it's a lot more. So then they came up with this idea, oh, why don't we use the logarithm then? All right, there's nothing like the theoretical physics type of these are not formulas directly derived from nature. These are mathematical functions helping us towards our needs, but they do not exactly match our needs because our needs are really biological, and here we don't know whether this is actually the way the nature prefers to weigh things. All right, so just treat them as heuristics, ideas that are good towards achieving the optimum, but they are not always perfect. All right, so this is the idea of breaking the linear scale and making it logarithm. But there's a problem with this, right? Because when the uh, frequency is 1, okay, if an amino acid occurs exactly 100% in that column, logarithm of 1 is 0. So whatever ratio you're taking, you're not going to get a negative number. And when you get a negative number, it's good that you can take, for example, minus 0.9 is better than getting 0 here, or minus 0.1 is getting better than 0 here, because you take the ratio against another negative number, so you make this minus 0.9, for example, is minus 0.01, you make it 90, plus 90 by making this ratio. But when the frequency is 1, the numerator is going to be 0. So whatever ratio you're taking, it may be some negative small number there, doesn't matter, your weight is going to be 0, because logarithm of 1.0 is 0. So this mathematical formula had also this problem. And there's a way to get rid of this by not allowing even 100% occurring amino acids. We are going to make sure that it doesn't exactly get the value of 1.0 as frequency by adding some, imagine, in addition to our n residues, we add another residue and make the total number n plus 1. And this 1 is some character that doesn't occur anywhere in our alphabet, just like the suffix 3 case, just like the dollar. So this is like an imaginary character. And if we actually look at the number of amino acids in that column, it's going to be at most, if an amino acid occurs in all of the n sequences, this is the maximum ratio that it's going to get, and which is not 1. Therefore, we are going to, the maximum weight we are going to get is going to be ln 1 over n plus 1. So the smallest one is, so is going to be 1. In the case, actually, the smallest one is 0. But that's also a problem, right? If for example, a frequency here is 0, it's ln 0. That's also a problem. It's going to be negative infinity. ln 0 or log 0, whatever, natural logarithm 0 or log 0, which power gets 0, what power of 10 base or natural number e, the number e gets you 0, it's minus infinity. E to the minus infinity is 0. And therefore, if this frequency is 0, we also have another problem. We get a mismatch penalty. So imagine you have a weight of minus infinity, okay, for that position, for that 0 frequency, when you use this ln term, and you multiply this with that, whatever additions you have coming up later, this minus infinity is going to dominate them all, and your mismatch penalty is going to be minus infinity. It's going to dominate that. So that's also a problem. Okay. Oh, by the way, instead of using the frequency directly, they use 1 minus that frequency. And when it becomes 1, that's a problem. So when it's 0, it's not a problem. ln 1 is 0. We get 0 from the contribution of that weight. So if we can change that formula, we can get rid of this minus infinity actually with this formula. This formula immediately takes care of that minus infinity issue by, instead of weighing the frequencies like this, when you say 1 minus fub, it's going to get closer to, when this part gets closer to 0, it's going to be more negative, closer to infinity, right? So since this is a negative number, my previous formula actually was flawed because the weights were reversed. If I use the frequency directly here, ln that frequency divided by this one, larger frequencies will get smaller positive weights. To avoid that, this this part here inside should be 1 minus the frequency, because closer it gets to 0, the more negative it's going to get. And since it's divided by this negative number, the larger it's going to get when this 1 minus frequency gets closer to 0. So the correct formula should be this. And again, this will have a problem when we have 100% frequency, because it's going to have a infinite score, positive infinite, because minus infinity divided by some negative number is going to be a positive infinity. So we will have again the infinity problem when the frequency is exactly 1.0. We don't have the problem when frequency is 0, when we don't have amino acid, when a residue type B occurs 0% in this column. ln1 is going to be 0, therefore its weight is going to be 0. So for amino acids that don't occur in that column, we have no problem. Okay, their weight is going to be 0 nicely with this formula. But amino acids that occur 100% in that column will be a problem, because they will now 1 minus 1. It will be minus infinity in the numerator. And to solve that, we can have this n plus 1, so that we make sure that no amino acid is represented 100% in that column. So these are just numerical tweaks so that our heuristic function works as expected when we're computing these scores. Okay, again, as I said, these are just heuristics. Don't forget about this. And if at any time you're confused about this, please read the book chapter on this, the chapter 6 from the textbook, which explains all these things in with some accompanying text, which will help you understand the material better. So if you let me show where they are. So all these things are frequencies. Everything on my slides are actually parallel to what this book says. All right. So all this first type, I mean, even the terminology is the same. So why this formula is used, okay, and why then we are going to use something else, a different formula. So the book is a really nice material, this chapter, to understand the subject matter better. Okay. So yeah, I'm referring you to the book if you have any difficulty in understanding these parts. And another heuristic that can be used to compute these MUAs is to borrow ideas from the scoring matrices, how they were computed in the first place. If you remember, the scoring matrices were computed as log likelihoods. Then why don't we also use log likelihood to compute the match-mismatch scores instead of referring to the scoring matrices directly? In all the previous cases, this SAB here, there's a term that says SAB, and here also. This is the actual scoring parameters we used. Whether it's this SAB is referring to Blossom 62 matrix or PEM matrix or nucleotide match-mismatch scores. Now, this one is really a radical change from the previous way we compute this position-specific scoring matrices. It completely gets rid of Blossom 62 or PEM and says, why don't we compute by looking at our profile? Why don't we compute the position-specific scoring matrices from scratch? I mean, without referring to Blossom 62 or PEM, which is going to be really specific to this family. And how we compute these things, so here QUA, again, the subscripts are the same. U denotes the column or the position in the protein sequence. So it's saying that what is the match score or mismatch penalty of aligning UA to column U of that profile. If you look at this, it says that how much that amino acid occurs in your profile or in nature. So it's if it occurs more in that column, this QUA is single observed occurrence of A in that column. If that A occurs more frequently than random, so PA is just random occurrence of that amino acid A, wherever, in whatever index or position. So this QUA usually directly is the frequency that we use, for example, it occurs 60%. But this amino acid in nature, for example, if they were all equally likely observed, it's going to be 1/20 ratio, okay, 0. Or 5%. So each amino acid occurs 5% if they were all equally likely. If this amino acid occurs 60% in this column, it's going to be 60 divided by 5, which is 12. And when you take the logarithm of 12, it's going to be a positive number. So it's going to be a match score. But if the observed occurrence of that A, letter A in that in that position is less than the expected occurrence by random, then we are going to have a mismatch penalty. It's going to be a mismatch. If you try to put A in that column, in the profile, it's observed even less than what we are expected by random, so you're going to get a mismatch penalty. So this idea is exactly the same as how the Blossom 62 matrices are computed, but this PA could be coming from not the good thing about this method is that instead of the natural occurrence frequencies of amino acids, I mean the frequencies of amino acids in nature, we can actually obtain these PAs specific to our family by looking at what is the probability of observing this type of amino acid in that family. Okay, so the scoring that we use may be really fine-tuned to the protein family that we are currently studying. So that may be a better way to do. Okay, but you see directly the problem right here, the mismatch penalties. If, for example, an amino acid type occurs with 0 frequency, if this QUA, if we directly use the frequency, if amino acid type A occurs 0% in that column, we now have this log 0 problem, which is going to say that the mismatch penalty to try to align some amino acid type A to that column is going to be minus infinity. Intuitively, it's like this. If in the family, in the protein family, there is no amino acid type of that type in that column, it's impossible to align a new sequence with that character to that column. Okay, it's because it's going to get a minus infinity alignment score at the end. Okay, so it's not going to dissolve. So it's really strict. This kind of a scoring mechanism is so strict that if it doesn't allow mismatches, in the sense that you cannot have a new sequence with just new amino acid type in that column aligned against that part in that protein family, which may make maybe sense in certain applications if you want to just follow the protein families. I mean, you don't want to have a new amino acid aligned to that and any column of that protein family. It may make sense, but it's maybe too strict. What if we have a new protein sequence which is going to be 99% similar to the other, but there's a mismatch, and we have to put that mismatch in a column where it's not observed before. So it will not be possible to align it like that if we have this minus negative mismatch penalties. So minus negative mismatch penalty is too harsh. So this formula, therefore, has to be updated, similar to the one we had here, where we introduced a new one, a single character that didn't occur anywhere. What we may assume is that we may assume every amino acid type occurs at least once in every column. This assumption, this statement that I just made, which says every amino acid type occurs at least one in every column. If you have, this may be introducing too much noise, right? I mean, if you only have 5 sequences in your family, it's like adding all amino acid types occurring once in every column. You're just making your alignment, multiple sequence alignment, a noise, a bunch of amino acids appearing in every column. So we can actually add these counts as not in integer units, but also as like partial real valued units. Instead of, for example, imagine if I have 5 sequences in my profile, I assume that every amino acid occurs 0.05 times in every column. So I'm adding 5. So here the count, the noise that I'm going to be adding, so let me write it here. The noise I'm going to be adding, if I have just 5 sequences in my family, okay, 5 sequences. Now I assume in every column, every amino acid type, okay, A, C, D, E. So every amino acid type occurs at least 0.05 times. So if you sum all of them up, if you sum all the counts, it's going to make 1, right? So into this 5, the actual counts, they will also count the actual occurrences 1, 1, 1 each. So then the total count is going to be increased to 6. So this noise part is just 20%. It's like you have added 20% noise. Since you're allowed to add these real numbers in any amount you want, what if I make my pseudo counts 0.005? In that case, they will all together, all these noisy added amino acids, they're going to make up 0.1 in total. So I will be adding just this much noise, my total counts at the end, in addition to the actual counts of amino acids at every column, I'm adding 0.1 of noise, representing each amino acid with certain amount, okay? And this ensures that the count of, for example, if A doesn't occur anywhere in the actual family, this FUA is going to be at least 0.005. Okay, so it's not going to be 0, which will avoid this negative infinity. If you plug this one this time in your formula, you're going to get this 0.005 over its expected occurrence. For example, if its expected occurrence is 0.01, so this is going to be 0.1, and log 0.1 is going to be -1, for example. You're going to get a negative mismatch penalty of -1. This may indicate a mismatch penalty of -1, but you'll see we have avoided the problem of negative minus infinity. All right, so these are called the additional amino acids that actually are not observed in my column, but the assumption that all of the types actually occur a small, tiny amount. To avoid this negative infinity problem, these are called pseudo counts. Pseudo counts, like virtual counts. They do not exist actually. Pseudo counts, they're also used in profile hidden Markov models to allow transitions from certain states. Otherwise, we just only allow a fixed transitions. We are going to see these pseudo counts will also be observed in this, which actually you see here. Let me show you in this short paper again. If you take a look at this figure, look at this. My protein family contains V, 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 F, and I in the first column, right? Look at the frequencies. These are the frequencies that occur in every column. V has a very large frequency. The bar here shows its frequency. This bar here is probably linearly proportional to its weight. So there's some V, there's some I, there's some F, and all the amino acid types, they're non-zero. They have a very tiny thin bar that shows amino acid type A also is possible to be observed in the first column. So these are our amino acid types, A, C, D, E, F, G, 20 of them. And we give tiny bit of everything to every column, and the observed occurrences are increasing these frequencies. So if this V, for example, is this bar's length is larger, much higher than the occurrence of V by chance, this log likelihood is going to give me a positive score at the end. All right, so this is basically what it is, and this slide is talking about that minus infinity problem, and this pseudo count. We can add 1 or we can add 0.01. We can, whatever we are adding here, and their summation is here. Instead of if this n is a small number, adding 20 to n is, as I said, adding too much noise. If n is just 5 and you assume 20 other amino acid types also exist in that column, it's too much noise. So we can actually add that a small number of small amount, not 20. We can just have them 0.05. And this is also something nice. Look at this right-hand side here. Instead of using 0. For example, 0.5 for all of them, instead of using the same amount of count for every type of amino acid, why not introduce these pseudo counts proportional to their actual occurrence in nature? For example, it doesn't make sense to have at these pseudo counts the same amount for tryptophan and glutamine. They may have different observation frequencies in nature. So add these pseudo counts proportional to their frequencies in nature. So this also makes sense. So we are adding noise, but this noise follows nature. Okay, and the whole idea of this right-hand side is to avoid negative infinity, because if this one is 0, when this one is 0, what are we going to have? 0 divided by whatever it is, and we are taking the logarithm of this, QA divided by PA logarithm, right? This was our PSSM, and if you take the logarithm of 0, you get negative infinity. The only reason to add this right-hand side, these pseudo counts, is to convert this negative infinities to some negative score, like -5, -6, -6.1, whatever the negative value they're going to be. So this better formula is what we may use for computing QUA and to compute, and we are going to plug in QUA here. This PA can be the amino acid frequencies that are observed in our protein family, so it may be specific to our protein family, which will make this really like a position-specific scoring matrix tuned for our protein family. Okay, and all these scores, when you compute MUA, up to this point in the slides, we are still doing the same thing. We are aligning a profile. We just converted these frequencies to first pre-computed score or values, match-mismatch scores. And instead of using the frequencies directly, we just, the same thing. This MUA is the same pre-computed thing we did earlier, and we just use the better formula to indicate those. And this is what position-specific scoring matrices are. And the way we can view, the one way to view this profile or position-specific scoring matrices as logos. These are also called sequence logos or web logo. You can go to this weblogo.berkeley.edu, and there's also a Python package logo or sequence logo, something like that. We actually use this in our, we are going to have an applications note appearing in Bioinformatics soon. And we are looking at some binding motifs and trying to figure out in certain sequences these motifs, and we use the similar sequence logo representation. And actually, yeah, let me just show you that one too. The name of our tool is going to be Motif Genie. Motif Genie GitHub. GitHub. Yeah, it's actually showing Motif Genie. Where it is? Yeah, it's here. So it's not even indexed by Google yet. But let me just show you the logos here. So we generate something like this. By simply, you just give these frequencies of your sequences, and this Python tool really nicely. So these may be our sequences. Again, no match or mismatches. So imagine we were looking for a pattern, and we have found these alignments with certain similarity score. As you can see, they're differing in certain positions. But if you look at, if you try to build, which, for example, 1, 2, 3, 4, 5. The fifth position is mostly C in this thing. So if in this motif, so if you do that, maybe this example may not be an output of this, but I just want to show you which Python package is that. Yeah, Logo Maker. Its name is Logo Maker. So if you're interested in this and you're coding in Python, if you you may use this Logo Maker package to have your visual logos not very easily from a given frequency matrix. All right, so let's get back to the slides. And these weights, as you can see, the weight of a font, the size of a font is computed by what I told you before is entropy. This is the entropy formula. Minus probability, frequency times log of that probability. So this gives us an entropy, and we use this entropy as a negative weight because the smaller the entropy, we want smaller entropies. The smaller the entropy, the more conserved that column is. So we want smaller entropies, and this IU, which may be a weight, and we also multiply it with an individual's frequency in that column to actually give weights to these phones. And it will tell you nicely for non-conserved columns, the entropy is going to be large. Therefore, the total sum of the columns are going to be quite small compared to conserved columns. It will give you a way to immediately see which columns are conserved. All right, so now I'm going to give an introduction to profile hidden Markov models, if I'm not mistaken. Yeah. And then I'm going to finish today's lecture, and we're going to continue with profile hidden Markov models on Thursday. Now, this is, now we have talked about, up to this point, we have talked about position-specific scoring matrices, how we can score a sequence against a profile. Now we are going to see an alternative method to represent a family of protein sequences, again given to us as a multiple sequence alignment. They, as I said, they are. This is a technique borrowed from speech processing, speech recognition, and this profile hidden Markov models are this term or PHMMs are specifically used to indicate profiles of protein sequences or DNA sequences. Okay, so first I'm going to talk about in general what a hidden Markov model is. Before going into profile hidden Markov models, I'm going to describe what a hidden Markov models is, what its parameters are, and how we can use it to answer different questions. So I'm going to come back to here. Let me get back to my black pen color. Okay. Profile hidden Markov models are used to model some time-based, time series phenomena. For example, I first do this, then do that, and then do this. Okay, a series of events, a sequence of states. These states are actually what are hidden. The name hidden Markov model is coming from the fact that whatever process this is, as an observer, we cannot observe these states directly. But each of these states, when these states are visited by this phenomenon, I'm going to give concrete examples. When these states are visited, they also emit symbols. Okay, but these symbols that they emit are probabilistic. They come from a probability distribution. Let me give you an example here from some concrete case so these states and what they mean is going to be better understood. I always give this example in my lectures. I think I read it in Wikipedia. So it's an example related to zebras. Okay, so imagine we are some zoologist or behavioral biologist which study zebras and their behaviors. And these states are going to indicate their emotions or internal their feelings. All right. For example, a state, a zebra, maybe in a hungry state. Hungry. Let me first write the hungry. A zebra may be hungry, thirsty. So in this model, we are going to have some assumption simplifications. We are going to assume that a zebra is in one of these states at a given time. Okay, angry, afraid, tired. All right, so imagine we have these states. Now, these states, we cannot talk to zebras and we cannot ask them, are you angry or are you afraid or are you thirsty? So these states therefore are hidden from us. But what we can do is we can observe zebra's actions, right? A zebra may run, walk, maybe stand or lay down or eating, drinking, drinking. So these actions are symbols that we may observe out of these states. For example, is it possible that zebra is running when it's afraid? Yeah, most probably. But is it also possible that it's standing? Yeah, it may, but with a low probability, or maybe a zero probability. But when it's tired, for example, when it's thirsty, it may walk to find some. So the probability to observe walking when it's thirsty, it may be non-zero. It may be drinking. So what I'm trying to say is that all these symbols that you have here may be observable in multiple internal states, but with different emission probabilities. These are called emission probabilities, which means that when the zebra's internal state is this, it may do this action. And this is the action that we are observing. Each state may emit multiple actions, multiple symbols. And another important thing in this hidden Markov models is that there are transitions between states. For example, after it's tired, and we, for example, observe some eating, or maybe not eating. After it's tired, it may go to the hungry state. After hungry state, we may go to thirsty state. And from hungry state, we may also go to afraid state. Imagine while we're eating something, we come up with another animal which is a threat to us. We may go to the afraid state. We may go to afraid from thirsty as well. From afraid, we may go to tired if we run a lot, if we observe this run action. So in these states, we have certain observations are outputs, and there are transitions between states, and these transitions are also probabilistic. All these things, this hidden Markov models, there are lots of probability densities which are discrete probability densities, because the number of states are finite. In a hidden Markov model, when it's given to you, you're going to be given a number of states. Okay, the states, their name are also going to be given to you. I mean, when I say hidden, they're hidden in case of, for example, when we are observing a zebra action. When we observe a zebra for a week, and we think that its behavior is governed by this hidden Markov model, when we're observing that zebra for a week, we're only observing these actions, these outputs. The emitted symbols are observed, but these states are hidden from us. But there are finite number of states. So from one state, you may go to any other state. Okay, so then these, from this hungry state, where we are going to be here in the next state. In other words, the probability to be in state I plus 1, given that you are in this state at, this I plus 1 is, let this be our time unit. If at time I, we know that we are at probability we are at this particular state, the probability that we're going to be at this other state at I plus 1 is a one-step transition probability. And this one, for all possible Si plus 1s, for all possible states, this one is equal to 1. So it's a probability mass function, meaning that our probabilities, we have to be at some state. If you're in, and there may also be self transitions that you may be at the Hungry state at time I. At time I plus 1, time point I plus 1, you may still be at the Hungry state. So there may be self transitions, but these transitions have to add up to 1. And the emission probabilities also, when you're hungry, you have to emit some symbol. So at every state, there is something we observe. Even if it's nothing, standing still or laying down, it's still an action, and we observe here. So at every state, there is some action that is emitted, and we observe that, okay? And also, there is another probability distribution, which is at time 0 or at time 1, whatever our starting time is. At t is equal to 1, which state we start this model. Since we are going to model a time series step, there should be an initial state that we start this in. And this is also a probability. We may start at tired at the for example, we start our observation at 8 a.m. every morning. So what is the probability that it will be hungry at 8 a.m.? What is the probability that it will be tired at 8 a.m.? Maybe it's a very low probability since it's probably slept through the night. It may be the probability of being tired at the beginning of our model may be low probability, but it's still a probability. Okay, maybe it ran all night long, so there may still be some probability of being tired. So what state we are going to start our running our model, the probability of start states, again, it's a probability distribution over all states. It's a probability mass function. Again, we have finite number of states, and they may be not equally likely depending on what you're modeling. Which state we are going to start is another probability. Now, given this model, I'm going to quit shortly. Given such a model of a hidden Markov model, we may ask questions like this. If I observe a zebra for 1 day and I observe these actions, run, every hour, imagine at the beginning of every hour, I observe what the zebra mostly did in the previous hour, and I write that here. It run, walk, then ate something, eating, drinking, and then run. So we may ask, given these observations, if we're given this model with all the associated probabilities, we will be able to ask this question. What is the most likely sequence of internal states that produce this output? Okay, so we may try to infer, given this, if this is the correct model, what is the most likely sequence? There may be multiple states. There may be quite many different sequence of state transitions that produce the same output. Okay, so this is not for certainty. Okay, run, walk, eat, drink, maybe an output of different sequence of states. But we are interested in which one is the most likely, with the highest probability associated with. Okay, there may, this is not for certainty, but what is your most intelligent guess that produced these states? That may be one question. Or what is the probability that this observation is coming out of this model? Maybe we may have 2 different models for 2 different zebra families in different parts of the region, and they may have different behavioral models, and we see a lost zebra, trying to observe it and trying to figure out which of these families this zebra belongs to. And we may also ask, what is the probability that this will be observed from this model? So we are going to talk about all these things, or I'm going to continue this example and talk about what kind of questions we can answer with the hidden Markov model. And then we are going to talk about extension of this general hidden Markov model to protein sequences. there is no time here, but our sequences, protein sequences, have an order, right? From the first position to the last position, they're also ordered things. So we are going to use this order and model it as if it's time to represent those protein sequences also as hidden Markov models. All right. I will be happy to stay to answer your questions. So our regular office hour time is just after this class. I'm going to stop recording now. And